Hello and welcome to the C programming lecture on functions. What is a function? At this point, we've tangentially covered what functions are. We've been using them, we've been you've seen actually an implementation of a function, but have never created your own. So in this particular lecture, I kind of wanted to go over what a function is and how we can create our own functions. So a function is just a block of code that it can be invoked with parameters. We've seen this by using printf, which we've used a lot. Also other types of things like macro functions. There's other types of ways that we can use something that looks like functions using our preprocessor, which again was the macros. So a function prototype is a definition of a function, and it's optional depending on the placement of the actual definition of a function, the actual implementation of it. So on the left here is a abstract function definition, typically referred to as a prototype. So we have a return type with a function name and some parameters. And again, here is the actual implementation. So on the right, this is a concrete example. We have an integer return type for a function named myFunction with the parameter of x, which is a int, and the implementation underneath. So here's an example of a function. Now I wanted to give you a kind of, quote unquote real world example of what a function may look like. So I went ahead and added a structure to it, which is our vec2 structure. So we have a vec2 structure, which is defined on lines 4 through 8. This should seem relatively familiar. And then we also have a magnitude function here. So this magnitude function is the definition of how the prototype of the function, and on line 29 is the actual implementation. So the actual implementation is using the square root f function, which is defined in the math.h header, which is included in line 2. So what we're doing is we're just taking the actual magnitude of a vector, which is just the square of each component and square rooted. So this is, basically Pythagorean's theorem. So anyways, that set aside, I just wanted to use this example to show you how to create a function. So, and how we invoke it and how we use it. So here's our type on line 14. This is what we create. This is our variable v. We print out the vector, which is 3 and 9. So what we're doing is we print it out on line 20, and then we have a new variable called float, and it's d, because our actual function returns a float value. So that float value that's returned gets stored inside of d. When we invoke this magnitude function, you can think of it as jumping down to line 32, doing this computation, and then returning that value to the variable d. And we can see that that is what is output on line 24 and our second output line in our terminal. So function scoping. So we previously learned about scoping, and the same rules applies to functions as well. And we kind of talked about it during the scoping lecture, and we said that we would discuss more about functions and function scopings. So variables that are parameters are declared within the body of a local scope to a function. So whenever the parameter, whenever it's defined, is only actually defined within the scope of that particular function. These variables will be placed on the stack memory segment. That being said, whenever a function is calling malloc, that memory is being placed on the heap. So again, this kind of comes back to our memory allocation and deallocation. So in order, if you're ever allocating a particular block of memory inside of a function, you want to make sure you keep track of it, because that memory address will at some point potentially need to be freed. Okay, so here is a kind of interesting point. So passing values and passing pointers to functions. So oftentimes, especially nowadays, we don't really say passing references because it has a different context as it had in the past. So in the past, you would usually hear people say passing values versus passing reference. And what that meant was, you're either passing a value or a pointer that has a pointer to a value. Now that in several different languages, people have actually taken the term reference and made that reference actually mean the actual variable memory address rather than a pointer to it. So that has a different context. So I wanted to be explicit as to what I was saying, especially because these new languages that have come out have kind of taken over this reference keyword, which has a different meaning than what it was used in the past. So our prior example shows passing variables by value. So what that means is we pass a value in, and that local scope variable that we have inside of our function, that parameter, gets a copy of it. It's inside the stack. So if that's manipulated, the local value is manipulated. So oftentimes though, programmers would want to pass in an address of a variable and have an operation done on a particular address. That's when pointers come in and it becomes particularly useful. So the variable actually inside the parameter list that is a pointer still lives on the stack. However, that pointer's value is a memory address that is referenced somewhere else. So whenever you manipulate the underlying memory address that is pointing to, you're actually manipulating the variable that was passed, that indirect access that you were passed into it. So here's an example of pass by value and a pointer to functions. So for instance, let's use the same example that we had before. So basically lines 17 through 25 are basically the exact same thing as we had previously. However, we're now going to introduce something on line 13, a new function called scalar multiply. So what we're going to do is our first parameter is actually a pointer to a vec2, and our second is a integer value of s. And what we're going to do is we're basically just going to, on line 40, we're going to take that particular pointer, we're going to dereference it, each of its components, so each of its x and y values, and we're going to multiply it by the actual variable s value. So you can see here that we're going to scale it by 10. Scale in vectors just means take every component and multiply it by that particular integer value. So that's exactly what we're doing here. And you can see that when we do that, we're actually, there's no equal sign, we're passing the address of this v, and it's actually manipulating the underlying memory address inside of this function on line 40. We're by using that indirection operator, the pointer, the reference operation. So again, a brief review of functions. A function is an invocable block of code. A function can contain a prototype that is the definition of how the function signature, quote unquote, works. So a function contains a scope similar to what we learned previously about scopes. The function parameters can either be passed by value or by a pointer. Sometimes you will hear this either passed by value or passed by reference, but again, nowadays that term reference has a different context as to what it had in the past, so it's often better for me to just be explicit and say pass by pointer. So function parameters and local variables are stored on the stack. This is often referred to as a stack frame. So I mean, there's other things inside of a stack frame, but those in particular are the local context of a function will have a stack frame. So let's go ahead and just go into code, create some functions, and mess around with this stuff using very simple examples. Okay, let's go ahead and start out with some code examples for functions. So we're going to keep this pretty brief and simple, just because there's no need to add some complexity to these examples. So first and foremost, let's go ahead and get some of our boilerplate code set up here. Again, this is pretty standard at this point. We just want to write our hello world program to ensure that we know that all of our tooling is working. And I think this is especially important when you're first starting out. Regardless of the language or whatever you're using, just get some type of boilerplate code up and running in order to make sure your environment's working. All right, so let's go ahead and hop into what is it that we're doing. So the functions. All right, so let's go ahead and just make a type def of a structure. And going along with kind of the example here, we'll make a structure. Let's just call it a vec3. So we use vec2 in our examples. We'll just say vec3 here. And let's just make them integers x. Let's just say int y, int z. And again, we could use a union and have all that fancy stuff. Let's just keep it nice and simple here. All right, so we have a vector. Now what I want to do is let's just make a void print vec3, something like that. And maybe it just takes in a vec3 structure like this. And let's make another one that's like something along the lines of void. Let's have it return. So it returns nothing, and it also it's going to scale our vect3. We could actually, since we didn't show this before, let's actually return a new vect3. So now this is going to be interesting, and you'll see what I'm talking about. We're gonna have a vect3 non-pointer passed in. We're gonna return a vect3, and let's go ahead and implement both of these functions, or at least add their stub code here, like so. And first, we'll go back up to main. So let's do vect3 v equals, and let's just make our x component equal to 1. Our y component equal to 1. Let's just make it all equal, every single one equal to 1, so that way we know that they're all the same. All right, great. So we're just going to compile and make sure we're good. Everything's fine. Now our print statement is, let's just do this real quick. So print vect. So this should be fairly simple. We're going to just say inside of x, %d, y, %d, and then our z, %d. New line, and then it's going to be v.x, v.y, maybe, v.z. There we go. All right, so the next thing we're going to do is we're going to add a print statement. We're going to just say print vect3, pass in our variable v. And this is exactly what we expect. We're going to print that out. Now next, what we're going to do is we're actually going to have it return this scale. We need this to actually have an integer. We'll call it x. And we'll actually change the signature up here in x, like this. We'll just say vect3 non-pointer to be explicit. Non-pointer. We put non-PTR. And the other one we're going to do is we're going to say pointer, right? So this is going to be a void. And we're going to say PTR. Like so. And actually, we're going to just define it up here. So that way it gives you an example of how we may, how this may work using something else, like using a different type of syntax here. So as you can see, we do not have a prototype, a definition, or like the signature of the function declared. We're actually declaring it above. And this is what I'm talking about, where your ordering matters. If it becomes before where your use case is, it's okay to place it, but then things become a little weird. So most people like to just have the actual signatures separated, like the prototype separated from the implementation. But I just wanted to show you a variation of this process. So what we're going to do is say v.x, v is equal to v.x times x, and we're basically going to do this for the next two components. So this, what I'm showing you here, is a particular way of, there we go, setting up our code to return a particular vector struct. Now you can see here it's it doesn't know what a return vect3 is. So what we may need to do is actually assign this a value. So we just say, vect3 vect3 v is equal to this, and then we return v. So gcc main.c, it's saying v redeclared. Yes, so let's just say result. Let's just make it r. There we go. All right, no more redeclared definition. That was my fault. So, all right, what we're gonna do now, we're printing it out. Let's go ahead and scale it. So in order to scale it, we need to actually reassign it with the non-pointer function because it's returning a new structure. So when you think about it, we're passing in a structure and an int, and then it's returning us a new structure. So we have to overwrite that value with the new values inside. We're not actually manipulating the underneath values. And you can see that, for instance, if I did if I just did a lone scale non-pointer like this, and then let's say I pass in v and the number, let's just say 5, which all the components should just be 5 now. if I try to reprint that, you'll see that we get 1, 1. Now, what I need to actually do, like I said before, is redefine our actual result. So we can restore the value into v here because it's actually returning something. And now you'll see it's all 5s. So perfect. Now what we can do is, what we should do is now say, all right, we have a, so we have an implementation for non-pointer. Let's go ahead and do the implementation for pointer. So the implementation for pointer is going to look fairly similar to this. So what we're going to do now is we're going to say v x is going to be equal to, we can just do shorthand for times equal x, and we can do this for the rest of the components, like so. And it will manipulate the underneath value, and now we can do print v, and then we can use the scale pointer function. And what we're going to do is say v, and then let's just scale it by 10. So we had 5, 5, 5. Now it should be at the value, so it needs the address here, that's why. So it should be now 50, 50, 50, right? Because we're scaling this underneath. So you'll see that passing by pointer versus by value, you know, a pointer is a particular type of value, but that value is a memory address, and we're manipulating that underlying memory address here. So I just wanted to show you this brief example of how this could work. You know, I hope this gave you some insight into the context of what it means to pass by value or pass by value pointer.